Welcome to Ask and Learn.
Okay, well, in this problem we have an air standard cycle with three processes. And in the first part of this problem, in part A, we have to show the TS and PV diagram. So let's begin putting here the axis for our PV diagram. So this is the vertical axis, this is the horizontal axis, and this is going to be the TS diagram, okay? Okay, well, let's see. The PV diagram has three processes. The first process is an isentropic process. An isentropic process, as we know, is described by, how can we say, hyperboles. So we have this is not a good hyperbole. Let's put here the hyperbole of the isentropic process. So this is from point 1 to point 2. Now the second one is a process with constant pressure, and the process with constant pressure is described by this horizontal line and here. So this is the horizontal line and this is point 3. And finally, the last process is a process with that we're gonna say is a straight line because is a heat rejection that depends on the initial state constants. So this is going to be represented as a straight line. Oops, let's put in blue. A straight line from 3 to 1. Okay? And again, as we know, the heat enters the system in here and leaves the system in here because an isentropic does not exchange heat with the surroundings. Okay? So that's the definition of an isentropic process. So this is the PV diagram for this cycle. Now let's see the TS diagram. Always remember that isentropic process and TS diagrams are represented by vertical lines. So this is the vertical lines, which is an isentropic vertical process. Okay. So this is point 1. This is point 2. Now the constant pressure is going to be a hyperbole. Let's put it this way, from 2 to 3. And the final one, also a hyperbole, but a little strange one. And again, the heat enters the system here and leaves the system here. Okay, so this is the TS diagram, and the left one is the PV diagram. This is item A. Now let's continue with item B. In item B, we want to find the output. That is correct? Yes, that is correct. We want to find the output heat of the cycle. So the output heat, as we can see in the diagram, is represented. Uh, Actually, no, we do not want the output. We want the input. No, that is correct. The heat rejected. So the heat rejected is the output heat. Okay, so let's see. The output heat is going to be represented by the work done by the system, actually into the system, plus the change in the internal energy of the system. Okay, so First of all, what is the work? So the work, as we know, is just the area under the curve. So if we look here, the area is going to be this trapezoid. Okay, so this is the area that represents the output work. And if we calculate this, this is going to be, let's put here, the output work is just, sorry, P3 plus P1 divided by 2 that multiplies the volume, which is V1 minus V3, which is precisely what we have in here. Okay, it's the pressure 1, pressure 3 divided by 2, the area of the trapezoid. So the problem is we do not have the volume here. And since we do not have the volume, we can use the ideal gas law and change this to simply, let's put in here, P3 P1 divided by 2, which is equal R T1 P1 minus R temperature 3 divided by pressure 3. But again, there is a problem. We do not have the temperature 3. So let's find out who is the temperature 3 before finding out what is the output work. So to find what is the temperature 3, let's look in the cycle. We can use the transformation from 1 to 2 to find what is the temperature 2. And with the temperature 2, we can find the temperature 3. Let's see how we're going to find this. Okay? Uh, First of all, from point 1 to point 2, what we have is the temperature 2 is going to be an isentropic transformation. Therefore, it's just T1 P2 divided by P1 K minus 1 divided by K, where K is the specific heat constant. Therefore, what we have is 300 that multiplies 1000 divided by 100 to the power of 0.4 divided by 1.4. Calculating this, we find that the temperature 2 is 579.2 kelvins. Okay, now that we have the temperature 2, we can calculate who is the input heat, because the input heat, as we know, is going to be the enthalpy heat. So it's just M, this should be the mass, times the change in the enthalpy from point 2 to point 3. Therefore, this is simply mCp T3 minus T2. You understand why we calculate the temperature 2 before everything? So let's continue here. We have that 416 kilojoules, which is the input heat, is equal 0.5 times 1.005, which is the Cp, times temperature 3 minus 579.2. And calculating this, we find that the temperature 3 is just 1407.1 Kelvin. Finally, we can calculate what is the output work. So the output work is going to be 1000 plus 100 divided by 2. That multiplies 300 divided by 100 minus 1407.1 divided by 1000. That multiplies R, which is 0.287. And this is precisely, let me see, 251.4 kilojoules per kilogram. Now that we find what is the output work, we can finally find what is the output heat. Therefore, let's put in here, the output heat is going to be, let's see, negative M out. Remember that we need to multiply by the mass. Therefore, the energy is going to be divided by the kilogram minus M CV T1 minus T2, which is the change in the internal energy. Okay? So if we calculate this, let's do this calculation here. The Q output is just minus the mass, which is 0.5, that multiplies 251.4 plus 0.718, which is the CV, that multiplies 300 minus 1407.1. And if we calculate all this, we find that the output heat, or the heat rejected, is 271.7 kilojoules. Okay? And finally, item C of this problem, we have to find what is the efficiency of the cycle. So the efficiency, as we all know, is just 1 minus the output heat divided by the input heat. Okay, therefore this is just 1 minus 271.7 divided by 416, that is equal precisely 34%. And that's the final answer to this problem.